Welcome everybody, an AP Chemistry series of Unit 5. Today we will cover section 5.10 and it's all about multi-step reaction energy profile. As we can see, the name of or the title of the lesson is not new because we covered the energy profile. And you just remember that we drew the y-axis, x-axis. It was for, let's say, an exothermic reaction, and another one was for endothermic. We just remember that thing. So we're going to do the same procedure, but it's not for only one step reactions. We're going to do that for a multi-step reaction. So let's just have a look at the two equations right here. The two equations represent elementary steps for an overall reaction. So this is the overall equation. Okay, and these are the two steps of reactions. So we have step 1 and step 2. These two steps are represented in a graph, and the same thing is repeated. The y-axis represents the energy profile, whereas the x-axis represents the reaction coordinates or reaction progress. As we can see, we have two transition states. Okay, transition state 1, transition state 2. Since we have two transition states, then we have two steps. Say 4 steps, then you should have 4 transition states, etc. All right, so what does this graph can tell me? First of all, it can tell you about you have 2 steps for this reaction. And second of all, it can tell you that since we have two activation energies at that point, we can say which of these activation energies is greater in magnitude. So we can see that the activation in here for the first step is greater than the activation energy and the second step. And we can deduce that the first step is the slow step, whereas the second one is the fast step. So here it's the slow one here, and this one here is at the fast. Okay, since we determined that we have 2 steps, and we determined that the first one is a slow step, whereas the second one is the fastest, we have one more thing to be discussed as well. The reactant energy is less than the energy of a product. That's why we can say this reaction looks like an endothermic. And that's why we can say the first step of this reaction is endothermic, because we notice that the reactant energy is less than the product energy. So this is an endothermic reaction at the beginning. All right. And the second step here, we can see that this is the reactant with respect to the step 2, and this is the product. And we just noticed that this is an exothermic reaction at that point. So this reaction is composed of endothermic and exothermic reaction. So this beautiful graph can tell me a lot of information about overall reaction. Let's take another example. The question says, based on the following reaction profile, how many intermediates are formed in reaction HD? So first of all, you have to put in your mind the position of intermediates locates in B and C. And they're just like between the steps. So A represents we have 2 intermediates. Okay. Now, B says how many transition states are there? All right, so the number of transition states, by the way, represent the number of steps. So we have transition state number 1, transition state number 2, and 3. And sometimes the transition state are referred to the activated complex. Activated complex. So the number of activated complex refer to the number of steps. So here we have 3 activated complex or 3 transition states, and that's why we have 3 transition states. Or the answer would be as 3 transition states. C says, which step is the fastest? All right. Okay, so I just want to get it closer to this one here. You just keep in mind that if you want to describe whether the slow or fast is based actually on the activation energy. So the activation energy for the first step is represented in this form, and here it's represented in this form in here, and the last one is represented in this form. This is reactant, okay, this is the activation energy. And from the graph, we can notice that this is the activation 3, this is the activation 2, and this is the activation 1. And we just noticed that the the smallest activation energy is activation energy 3, and that's why it's going to be the fastest reaction, because you just remember as the activation energy increases, the rate of reaction decreases. So as we can see, the third step is the fastest one, and then it's followed by activation energy 1, and then the second step is the slowest step as it has the highest activation energy, as we can see. All right, so the activation energy 3 is the smallest one here. That's why it's going to be the fastest. And it's followed by activation energy number 1 because it's like the second place. And finally, the slowest step is represented in this one in the middle. So the answer of C is 3 is the fastest one here because it has a very small activation energy. All right, let's solve D. As we can see, if we just get a closer look, we just notice that the delta H value locates between the reactant and products. So I just want to assign reactant and products for delta H1, and we can see here in step 1, like from A to B, we have reactant side and we have the product side. So the delta H is going to be between them, and it's represented in this form in here. Like here, it's the delta H1, the green one, all right? Now let's go to delta H2. Since we have reactant with respect to product, like this is a second step, regardless that the B represents the intermediate, but I don't care about the point. We have reactant and product. The difference between them is represented by delta H2, and it's represented in the green color, as we can see, like this is the green one here, right? And lastly, I have to assign the delta H3. So since here we have reactant side and this is the product side, then this is the delta H. Now, if we take a bird view look in here, we can notice that the amount of the green, which represents the endothermic reaction, like the first step is endothermic because reactant uh, energy is less than the product. Okay, so the product is higher. You can see that there is increasing in the energy to the products. And the same thing is repeated for the second step, which is also endothermic. You can see that it was the reactant side energy is less than the energy of a product, and that's why it's an endo. And the opposite for the third step, it's an exo because, like the reactant energy is greater than the products. You can see the products are less than. So if we just erase the stuff in here, the green first represents the endothermic, and this is another endothermic. So the overall energy is represented in terms of delta H1 plus delta H2 plus delta H3. We notice that the delta H1 and 2 are endothermic reaction, and apparently they look like a greater than delta H3, which is an exothermic. And that's why the overall equation is going to be an endothermic reaction. All right, so the green color, if you just take that in terms of adding these together, I'm gonna add this right here to be in the same level like this. Okay, so this is the green area that represents the endothermic reaction. Okay, whereas the purple represents the exothermic. So generally you can see that the green area, which is represent the endothermic, is greater than the exothermic, and that's why it's going to be endothermic